These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the info box. The address is www.freelance-teacher.com/videos.htm, or you can just use the link in the info box. Thank you. Well, I don't know exactly what the circuit looked like, but I can give you examples of the type of problems he's talking about here. First thing to keep in mind is that the lamp itself is a resistor. The lamp itself is a resistor. Now the question is, what's going to be the change in the brightness of the lamp? So let's say we start with this picture. I should have drawn a smaller picture. Now let's say in this new picture there's an extra resistor. What's going to happen to the brightness of the lamp? Will it go up or down? And how can we explain that?
So I have to think about it like the brightness is power, and so the power comes from, which one should I use, like I squared R?
That's a good question.
Depending what I have. I guess
we have to use whichever of these is most convenient.
Is that one VR? Is that one?
Yeah, so you tell me.
Or V over R.
Do you have your cheat sheet? Do you have a cheat sheet you've started working out?
Yeah. V squared over R.
And there's one more.
And IV.
We know the definition of power is work over time, but these are the applications of power that are useful for a circuit. Now, the way I remember this is, I think of the fundamental definition as power equals IV. So I think of IV like intravenous, just as a memory aid. And then where do these other equations come from? You can just use Ohm's law. So if you know that power equals I times V, well, you could plug in I times R for V, and that would give you this equation.
Yeah.
Or you could plug in, for the current, you could plug in V over R, and that would give you this equation. So if we remember that power is like IV intravenous, and then we know Ohm's law, we can figure these out, or you can have those in your cheat sheet. So which of these do we want to use? We want to use one of these that has the fewest changing variables. For example, some of these might have two variables changing. Well, that would be complicated and confusing to think about. So we want to pick one of these where only one of the variables is changing, and changing in a way that we know. So we might have to figure that out as we go along, which of those is the most useful form.
So I should combine the resistors?
Over here?
Yeah.
Okay, you could try that.
I don't really need to do that. I guess I can think about it.
Yeah, in this case we might be able to do this just by thought.
So in the series you add them, so there'll be more resistance. But now it depends which one. So if I put it into I squared, there'll be more resistance, less power.
More resistance, less power? Which equation are you using?
V squared over R.
Okay. Now the problem with that is we haven't decided whether V is changing or constant yet. Remember, we can't use these equations until we want to pick the equation where only one of the variables is changing and the other one is constant. We don't know yet whether V is going to be changing or not. After all, you could just as well have said that a bigger R means a bigger power.
Yeah, but is it because there's a battery?
Ah, that's right. So that makes sense. So you're saying that the voltage from the battery is constant. That's right. However, So that would be a good point. So what happens to our equivalent resistance when we add this extra resistor? Does the equivalent resistance go up or down? So what's going to happen to but we know that the voltage from the battery stays constant. So what happens to the power from the battery?
It goes down.
Good. Good. The problem, though, is the question didn't ask you about the power from the battery. It asked you about the power across the lamp. So actually, this kind of helps us to guess what the answer is, but it doesn't answer it directly because the question is about the lamp, not the battery. Although this would put you on the right track. Well, if our equivalent resistance is going up, what's going to happen to the current from the battery?
Some more current has to come in.
Take your time and work that out.
Or less current.
How can you figure that out? Now, this has nothing to do with power so far. If the equivalent resistance is going up, what's going to happen to the current from the battery?
Can I use Ohm's law for that?
Yeah, we'd use Ohm's law for that. So if the equivalent resistance goes up, what happens to the current?
V is IR, so then if the V is constant and the R goes up last.
What did you say was happening to I?
Down?
Right. We know the voltage from the battery is constant. So if the battery is perceiving a greater equivalent resistance, it's going to have to deliver less current. So we know the current from the battery has gone down. This current has gone down. So what has happened to the current across the lamp?
So that I can think of. Well, across the lamp, do we say that, so the resistance across just the lamp is the same?
That's true.
And then so
What's
the power
happened to
had
the current
gone
across the
down.
lamp?
The power went down if the current went down.
Let's hold off on power. We actually can't figure out what happened to the power until we know what happened to the current. Remember, the power, if we knew what happened to the power, we'd be done. The power is the last step. Since the current from the battery has gone down, what's happened to the current across the lamp?
That's good now.
Gone down. How do you know? Suppose that this current is 3 amps. Then what's the current across the lamp?
3.
Because they're in series. These are the same current. So if this current is going down, this current must go down because they're the same.
And the other resistor. They all go down, right?
Well, this resistor didn't even exist before.
Yeah. But if
But
this was
the
your
current
picture,
through this point on the wire has gone down. That's right. The
as long
current,
as there's only one path, they're all going to.
That's right.
What if there was I'm trying to remember now if there's another path.
and there's another path that would be more complicated. That's right. So we're going to have to get through that because that's some of the other questions are about. So let's take the simplest case first. So we know that the current across the lamp is going to go down. Now we can pick out which of these is the right equation to use. For example, should we use this equation? Well, no, we should not use this because we haven't figured out yet what happens to the voltage across the lamp. So this is not a good equation to use. Should we use this equation? No, because we haven't figured out what's happening to the voltage across the lamp. How about this one?
We know the I and we know the R.
Yeah. Has the R gone up, down, or stayed constant? Now remember,
across
now we're just
that
looking
lamp.
at the lamp.
Oh, so it's constant.
The resistance of the lamp is constant, but do we know what's happened to the current in the lamp? It's
It went down.
gone down. So what's happened to the power across the lamp?
Down.
Now we have our answer. So this would be the full credit answer. So this was pretty tricky. I think, so what was the part that was easy for us and the part that was difficult? The part that was easy for you was that I think you saw that these were the sets of equations to use. You saw that we had to use these equations. The thing that was tricky is to remember that you always have to be clear in your mind about which device you're applying it to. So there's a Ohm's law for the battery, and there's power equations for the battery. There's an Ohm's law for the lamp, and there's power equations for the lamp. There's an Ohm's law for the new resistor, and power equations for the new resistor, and those are all different from each other. So we always have to ask, well, whose power am I thinking about right now? And you can see that very clearly here. What happened to the total resistance of the entire circuit that the battery perceives? The total resistance that the battery receives has gone up. But what has happened to the resistance of the lamp? That has stayed constant. So we have to be very clear about when we're talking about the equivalent resistance that the battery perceives or just the resistance across the lamp.